All right, so welcome everybody to today's edition of the Quasiworld seminar. So our first speaker is Xianghui Shi, and he will talk about the ergodic theory of expanding Thurston maps and their subsystems. So please.
Thank you for the invitation. I'm honored to give a talk at this Quasiworld seminar. Today, I will talk about some recent results in ergodic theory for expanding Thurston maps and their subsystems. Okay, let's begin with some definitions. First, it's a Thurston map F is a non-homomorphic map, a branched covering map on a topological two-sphere. Here I denote by S2 with a finite post-critical set. Here the post-critical set I denoted by post F is a union of forward orbits of critical points of F. And a point P is called a critical point if the local degree is at least 2. Okay, let's consider such an example. This illustrates expanding a Thurston map with 4 post-critical points. They are A, B, C, D. The sphere here is constructed by gluing 2 identical squares along their boundaries, forming a topological two-sphere. So you can see the sphere in the right. Those 4 bucket points A, B, C, D are post-critical points. And we define the map F piecewise linearly. Specifically, we subdivide each square into 9 smaller squares as shown in the left picture. The map F maps each small square linearly to one of the 2 large squares on the right by scaling the side length by a factor of 3. And inductively, we can define F on each small squares. For example, if this small square in the corner is mapped to the big square in the front, then the next one, this small square, should be mapped to the big square in the back. And in this way, we can obtain a branched covering map F on the whole sphere. Now, which points are critical here? So, as shown in the picture, like those points, they are critical points. To identify them, it starts to count the number of small squares containing the point. So if the number is at least 4, then the point is critical. For example, this such point. It's easy to see that A, B, C, D are post-critical points, since each critical point is mapped to one of them. And in this case, the set of critical points is disjoint with the post-critical set. Okay, here's another example. And in this case, we start with 2 triangles and glue them along the boundaries to get a sphere. We subdivide each triangle into 6 smaller triangles. And similarly, the map G is a linear map on each small triangle and sends each triangle to the big triangle on the right. Inductively, we can define G on the whole sphere to obtain a branched covering map. Here, I want to remark one thing, that this map has a periodical critical point, because you see here, all those 3 points A, B, C, they are critical. And it's easy to see in this case, there exists at least one periodical critical point. It's one of those vertices A, B, C. And this point is, so this map G is different from the previous one. Well, in the previous case, there's no such periodical critical point. Okay, next, we define the notion of expansion for a Thurston map. So a Thurston map F is called expanding if there exists first a metric D that induces the standard topology on the sphere, and the second a Jordan curve C containing post-critical set, such that the diameter of n tiles shrink to 0 as n tend to infinity. here, this Xn is a set of n tiles, and each n tile is a closure of a connected component of the sphere minus nth product of the Jordan curve C. And here, this definition actually is independent of the choice of metric D and the choice of Jordan curve C. This definition is topological. Okay. So we say those two previous examples, they are expanding in this sense. And for each n, those n tiles for cell decomposition of the two sphere. In general, those cell decompositions they are not compatible. Means each high-level cell decomposition may not be a refinement of the lower level cell decomposition. However, this is true if the Jordan curve C is invariant. Here we consider expanding surface map F and the Jordan curve C with containing the post-equilibrial set. If C is F invariant, forward invariant means FC is contained in C. Then if we consider its nth product, then we'll have such relation. This gives us a Markov partitions, and this structure is very useful and important in dynamical system. However, such an invariant Jordan curve may not exist. Namely, there exists a system map such that there's no invariant Jordan curve containing the post-critical set. Remarkable results by Cano, Floyd, Perry, the Bonk and Meyer states that for each sufficiently large iteration Fn, there always exists a Fn invariant Jordan curve containing the post-critical set. So that's not too bad. Okay. Up to now, we haven't defined any metric on the sphere. So here is a metric D on the S2 is called a visual metric for F. If there exists a so-called expansion factor lambda greater than 1, such that first each n tile, the diameter of n tile with respect to this metric D is comparable to lambda to the power of minus n. Here, the constant is independent of the choice of n tile and the levels. Secondly, for all disjoint n tile, xn and yn, their distance is bounded from below by this factor lambda to the power of n. And similarly, here the constant is independent of the choice of types and or levels. And okay. The idea of visual metrics was inspired by the study of Gourmand hyperbolic group in geometric group theory. When we consider a boundary at infinity of a hyperbolic group, there exists a natural class of metrics known as visual metrics. Here is an equivalent formulation of the famous Canon's conjecture from a quasi-symmetric universalization perspective. It predicts that if the boundary at the infinity of a Gourmand hyperbolic group G is homomorphic to S2, then the boundary equipped with a visual metric is quasi-symmetrically equivalent to the standard Riemann sphere equipped with a spherical metric. Okay, and Sullivan introduced a dictionary which connects two areas of conformal dynamics. One is the iteration of rational maps, complex dynamics, and the other is the Klein groups. And inspired by Sullivan's dictionary and the interest in Canon's conjectures, Bonk, Meyer, and Helsinki Pilgrim introduced the visual metrics for expanding system map and have shown that for an expanding system map, it is conjugate to a rational map if and only for the visual sphere here S2 equipped with a visual metric is quasi-symmetrically equivalent to the standard Riemann sphere. Okay. Well, this geometrical connection is interesting. Today, I will focus more on the ergodic properties of expanding Thurston map, since my topic today is the ergodic theory of those maps. I understand that some of the audience may not be familiar with ergodic theory. So let me start by some basic definitions. We consider a continuous map T on a compact metric space X and a probability measure mu on X. This is the setting we will work within our talk. Now let's consider measure mu. We say that mu is T invariant if for every measurable A, the measure of A with respect to mu is equal to the pullback of A on the T. So in other words, a measure of A is preserved on the T. We say mu is ergodic if for every totally invariant subset A. Here totally invariant on the T means T inverse A equals A. Then the measure of A must be either 0 or 1. So in this sense, ergodic measures are quite special. If we donate by MXT the set of T invariant Borel property measures on X, then the set of ergodic measures they form the string point of this space. That is to say, any ergodic measure mu cannot be decomposed. It cannot be written as a non-trivial linear combination of other T invariant measures. Okay, and for each T invariant measure mu, we donate by H mu T as the measure theoretical entropy of T for mu. Roughly speaking, this quantity H mu T, it measures how chaotic the dynamical system is with respect to the given measure mu. So in some sense, it's quite similar to the Shannon entropy from the information theory. Shannon entropy measures the amount of the information. Here in dynamics, the measure theoretic entropy measures the degree of chaos. Okay. Furthermore, we consider we have the following variational principle. For any continuous function phi, which we call the potential function, we have the following equality. When we consider the sum of the entropy and the integral of the potential function. Oh, sorry. I thought no voice. Okay. Sorry. It's okay now or no? Oh,
Yeah, everything is fine. Oops.
okay. Sorry. I thought no voice, but okay. Here we consider if we consider the sum of entropy H mu and the sum of entropy and the explanation of this potential function phi with respect to mu, and we consider the supremum over the space of measures, then this supremum equals to PT phi, or the topological pressure of T with respect to mu, and with respect to phi. And we say a measure mu is an equivalent state for T and phi if this mu attains the supremum here. Equivalent states are very crucial as they capture the typical behavior of the dynamical system, and they are at the center of our study. Okay. Is there any question? Okay. My PhD advisor Xianghui initiated the research of aggressive Thurston maps. In particular, he studied the equivalent state of expanding Thurston map. Here, the setting is for expanding Thurston map and the holder continuous function. here here the holder is the definition is with respect to a visual metric, and he proved that there exists a unique equivalent state mu phi for f and phi. Moreover, mu phi is mixing and ergodic. In particular, the preimage points of f are equidistributed with respect to this unique equivalent state. And I want to remark that here the preimage points they are weighted by local degrees. Okay. Now what I could now I would like to move on to our first result about the continuity of the entropy map. Here the entropy map is defined on the space of invariant measures. It sends invariant measure to its measure theoretic entropy. Here the space MST is equipped with the weak-star topology. In general, the entropy map is okay. Here we can post such question: continuity of the entropy map. Well, in general, the answer is no. It's not continuous, because lower semi-continuity falls easily in many situations. So, I can explain this. Because you see here, we can approach this equivalent state mu phi by preimage points. Well, the preimage point has measure 0, but we can actually prove this equivalent state as positive entropy. So this means we can approach a measure of positive entropy by measures of 0 entropy. So in this case, you see the lower semi-continuity falls. So we turn to a weaker condition, say called upper semi-continuity. And this question is very interesting, and because if the answer is true, then it immediately follows that for all continuous potentials there exists equivalent state. So this means the existing part is almost free for free. Okay. This question has a very long history. Date back to Bowen. Here I list some of the results. Bowen proved the property for all entropy expansive map, and 1 year later, Mizrachi extended Bowen's result to asymptotic H expansive map. Okay. In rational in complex dynamics, Lubitsch proved the upper semi-continuity for all rational maps. In the area of smooth dynamics, Neuhaus demonstrated that for C-infinity maps on smooth compact manifolds, the entropy map are semi-continuous. In the context of expanding system map, Xianghui Shi shows that if there is no periodic equilibrium point, then the entropy map is upper semi-continuous. So here he assumed there's no periodic equilibrium point. And actually here, all of those maps in those 3 cases, they are asymptotic H extensive. Okay, but there are also negative results. In some situations, the upper semi-continuity of entropy can fall. For instance, in the context of CR diffeomorphisms with finite R, they are common examples. In dimension 4 is by Mizrachi, and later they provided a common example for all dimension greater than 1. Okay, and more recently for CR surface diffeomorphisms, Buzet, Krivest, and Sarig, they estimate the discontinuity of the entropy map in terms of Lyapunov exponents. So they added a new discovery to this direction. They posed a question: is the entropy map up semi-continuous for every expanding Thurston map? This question is actually the starting point of this work. We already know that.
Can I quickly interrupt, right? I mean, this is just relevant for maps with periodic critical points, correct?
Yeah, because we already know this answer is right for those maps without a periodic critical point. So actually, we supposed to answer for those with periodic critical point. Okay. Okay. So the challenge now lies in either proving or disproving this for those maps that have at least one periodic critical point. Okay. So we give the answer. The answer is no. So the statement is for let F be an expanding Thurston map, then the entropy map of F is upper semi-continuous if and only if F has no periodic critical point. And moreover, we can estimate the defect in the upper semi-continuity. Indeed, the defect is determined by the local degree of those periodic critical points. So periodic critical point play an important role in the upper semi-continuity. Here the key observation is that the local degree at the periodic critical point increase exponentially on the iteration. Okay, to simplify the understanding, let's consider a fixed critical point. As the map iterates, the local degree of this point grows exponentially. So in other words, near this fixed point, we can find an exponentially increasing number of tiles that get very close to this fixed point. So based on this observation, we can construct a sequence of measures. Those measures become narrow and narrow in the weak-star topology sense and convert to the delta measure at this fixed critical point. So we show that the measures in this sequence has positive entropy, and their value are bounded from below by a positive constant. Well, we know the delta measure has zero entropy, so this clearly shows that entropy drop in the limit. So we show that it's not upper semi-continuous at the delta measure supported on such a fixed critical point. So okay, that's the key idea behind the result.
So can I ask you a quick question about what you just said? So if the measure has no atoms at periodic critical points, do you then have continuity, or do you know anything about this?
My hope is actually yes, your question is related to identify the set of discontinuous
Yeah.
discontinuous points of the space, right?
Yeah.
The entry map is continuous as a measure if the measure has no atom at those periodic critical points, right? So I think my guess is it's right, but I haven't proved it.
Yeah. Okay. Thank you.
Yeah, like a more quantitative version. Yeah, actually, if I think you should add an assumption that the measure is ergodic. If you consider an ergodic measure, which will at this measure the entropy map is not upper semi-continuous, then we hope we guess this measure should be a periodic measure supported on one periodic critical point, periodic critical orbit. Yeah, very nice question. And Okay, our next second result is about entropy density of ergodic measures. So what's the terminology mean? A subset N is called entropy dense in the space MFT. If for each invariant measure mu, there exists a sequence mu n in this subset N, such that first this sequence converts to mu in the weak star topology. Second, its measure theoretic entropy of mu n converge to h mu as n tend to infinity. So you say this condition is a stronger condition than just dense, right? Not only dense in the sense of topology, but also dense in the sense of entropy. Okay. So we show that for every explaining system map F, the set of ergodic T invariant measures is entropy dense in the space of T invariant measures. In other words, one can approximate non-ergodic measures with ergodic ones with similar entropy and expectations. Okay, so you see this property is very useful. Actually, it has been used in large division theory and multifractal analysis. Because instead of directly studying a general invariant measure, we can with a small cost, we can transfer the problem to study ergodic measures, for which we have more tools to apply. For instance, like Birkhoff's ergodic theory. The idea in the proof is to construct a suitable so-called subsystem. I will provide the formal definition of subsystem later. Here we use its measure of maximum entropy to approximate the given invariant measure mu in terms of both topology and entropy. The main difficulty lies in the construction of such a suitable subsystem. Because due to the non-uniform nature of the dynamical system, the construction is far from straightforward. Is there any questions so far? All right. Now we have arrived at the core of this talk. So what exactly does the large division theory study? Let's start with the classical Birkhoff ergodic theory. It states that for an ergodic T invariant measure mu and a continuous function phi, we have the following equation holds for mu almost everywhere x in almost every point. Roughly speaking, it means the time average is equal to the space average. Here Sn phi is a Birkhoff sum. It is a summation of phi over the for nth forward orbit. There's another way to understand this Birkhoff ergodic theory. Suppose we consider a closed interval K, not containing this space average, this integral. Then the measure of this set will tend to zero as n tend to infinity. Here we consider a point where the Birkhoff average is contained in this K, and notice that this K does not contain the average. So Birkhoff's ergodic theory says that the measure of this set must tend to zero. Okay. So one natural question is that how fast does this sequence converge to zero? Okay, so large division theory studies such question, and usually we can show that the speed of convergence is exponentially. Okay, so roughly speaking, the large division theory it studied the non-typical behavior of the dynamical system. So she focus on those sets usually has very small measure. I hope this can give you a rough idea of what a larger distribution theory study. Okay, now let me give the formal definition. We say that a sequence of Birkhoff averages satisfy a large division principle if there is a real function I such that for every interval k, the following holds. So it's give you the exact exponents of the convergence speed of. So if we take logarithm and divide by n and pass into a limit, in the right is the rate. So it's the interval of the rate function I over the interval k. This level 1 LDP focus on the time averages for functions, here function phi, and the rate functions live on the real line. Actually, we can go further. We can consider level 2 LDP for measures, and where the rate functions live on the space of measures. As indicated by the name level 1, level 2, there is a hierarchy, namely level 2 directly implies level 1 by a general principle in large division principle called the concentration principle. You can directly obtain level 1 from level 2. So we will focus on level 2 LDP since it's stronger. Okay, here's the formal definition of level 2 LD, large division principles. Here we consider a sequence of broad probability measures on a topological space X, and usually this space X is a space of broad probability measure we denote by px. So this space is space of measures, and the sequence Kcn it's measures on measures. So in this sense, it's called level 2. So we see that this sequence can satisfy a level 2 LDP if there exists a lower semi-continuous rate function I such that the lower bound holds for all open subset G, and the upper bound holds for all closed set K. We have to write them separately due to the weak start topology of the measure space. Okay, and for some very nice subset, we can write them together to get an equality for which give the rate of the convergence. Okay. Okay, here I list some existing results regarding the level 2 LDP. First, this one is in TCE rational maps with Holder continuous potentials, and in our setting, Li proved the level 2 LDP for expanding certain maps without periodic critical point. Recently, there's a result in one-dimensional real dynamics, namely for topological exact interval maps. Interval maps means maps on Z1 interval L1 with Holder continuous derivative and only non-flat critical point. Now here's our main results for all expanding submaps with Holder potential. Here the potential is Holder continuity is with respect to visual metric. We establish level 2 LDP for the distributions of for 3 distributions. The Birkhoff average identified by sigma n, and the periodic point identified by omega n, and the iterated preimages omega n xn. Here xn is the initial point because you need to take preimage Okay, and we show that each of those three sequences satisfy a logic deviation principle. Actually, uh, they satisfy a logic division principle with the same rate function, namely they satisfy a same law, same probability law. Okay, I'm knowing the formal definitions for those three sequences is a little bit complicated, so I will not list them. You can find them in our paper. Okay, or we can discuss in the question part. And this level 2 LDP implies the following equidistribution result, and this resolves the question posed by Li in the previous paper. Okay, so as a direct corollary of level 2 LDP, we prove that for iterated preimages and periodic periodic points, they are equidistributed with respect to the unique current state mu phi. And I want to remark that here the weight of a point can be arbitrarily chosen between 1 and the local degree. So this weight are not which are non-trivial because we are dealing with general expanding submap, including those have periodic equilibrium point. So for those maps, this local degree can grows exponentially fast. So this weight may not be uniformly bounded. So it's non-trivial. Okay. Okay. The main difficulty in establishing the level 2 LDP can be summarized in the following two aspects. The first one is due to the presence of critical points. So then the dynamical system is not uniformly expanding, which is a well acknowledged difficulty in dynamical system. So to overcome this difficulty, we use the visual metric because the dynamical system behaves very well on the visual metric. The second difficulty is due to the lack of upper semi-continuity, as we already showed in our first result. So in particular, this means we cannot apply the classical so-called functional approach. Actually, okay. It's due to Kiefer, and this approach was crucially used in both the TCE maps and the expanding source map without the periodic point for those two class of maps to establish the level 2 LDP. So we cannot use Kiefer's result. So we use a different approach that does not rely on the upper semi-continuity. In this sense, our approach is more eccentric because we didn't use the entropy property of the entropy map. Okay. Since the statement of level 2 LDP is consists of lower bound and upper bound, here we state our strategy for them separately. For lower bounds, in one sentence, the strategy is to approximate invariant measures with tiles. And in proving lower bounds, we use the entropy density of ergodic measures. As I said before, by using this property, it suffers to consider ergodic measures instead of general invariant measures. And for ergodic measures, we can apply like Birkhoff's ergodic theory and the Xianghui and SNB theory. For up bounds, here the proof for up bounds is more difficult than lower bound. Because here the construction is more delicate and difficult. We construct measures whose entropy and expectations provide desired upper bound for the deviations. Here, how we construct such measures, we build suitable subsystems and apply the thermodynamic formula to construct the measures, and the entropy of the measure about and their expressions will provide suitable upper bounds for which fits our need. Besides, in the proof of LDP, we first consider a special case where there is an invariant journal curve. Then we prove for the general cases by considering sufficiently high iterations. So here we also use Meyer bound and their result. And then okay. Now let me explain the concept and give definition of subsystems. So here we consider let F be an expanding Thurston map with a journal curve C, satisfying that C contains a post-critical set. And a map capital F from its domain to S2 is called a subsystem of F with respect to the journal curve C. If first the domain is the union of some one tiles, so the domain of F consists of some one tiles of F, and the map capital F is just the restriction of the original map F to its domain. We don't by sub F, say, be the set of all subsystems. Now, similarly, we can define the set of n tiles of F. This is a formal definition. Roughly speaking, n tiles are here n tiles of a subsystem are those tiles which live under the Hilbert iteration of the capital F. And furthermore, we define the tile maximum invariant set associated to F with respect to C be the intersection of the unions of n tiles. Okay, I know this definition might seem a little bit abstract. So let me show you two examples. We have seen something like this before, but now we remove the middle tile from both the front and the back faces. So the domain of our subsystem F consists of two groups of one tiles, 8 on the top and 8 in the bottom. And here the subsystem F is just a restriction of the original map to the union of those 16 one tiles. Okay, and you can imagine that as you do more and more projects, it will gives a fractal-like structure, just like a carpet. In fact, in this situation, the living set omega in this case is just two standard shipping carpet glued together along their boundary. Okay, we can also consider subsystem that resembles the statistical graphic. We just start with triangles, and each triangle is subdivided into 4 smaller triangles. Similarly, we remove the middle triangles from each face and keep the other triangles small one tiles. So in this case, the domain consists of 6 one tile in total, 3 in the front and 3 in the back. And you can imagine, in this case, you will obtain a cascade on the iteration on the project. Okay. So next, we developed the thermodynamics formula for subsystems. Here we consider a subsystem F and continuous function phi. For each n, we denote by Zn as phi. It's actually the partition function to be the summation of exponential of Sn phi over the entire Xn. And then we define the topological pressure of the subsystem F with respect to the potential phi by this. So this P and phi is our topological pressure for this subsystem F. Actually here, this limit inf can be replaced by just a limit. We can prove this limit exists. Okay. Okay. So we consider subsystem F and a holder continuous function phi, also with respect to a visual metric. We establish the variational principle and show the existence of equivalent states for certain subsystems. That's the so-called strongly irreducible. They have very nice properties. For example, those two examples I showed before, they are strongly irreducible. Okay. And we show for those subsystems, we establish the variational principle and show that there exists an equivalent state which attends this supremo. But here you know that there's no result about uniqueness. So next things furthermore for strongly primitive subsystem, this condition is stronger than strongly irreducible, and on this stronger assumption, we can prove the uniqueness, and furthermore show this unique equivalent state is mixing and in particular ergodic. In addition, the preimages of subsystem are equidistributed with respect to this unique equivalent state. Okay. Let me summarize our contributions. First, we find a new factor that causes the breakdown of the upstanding continuity of the entropy maps. The second, we establish entropy density of ergodic measures. And this one, third one is the central part of our work. We proved a 4L2 LDP for all expanding system maps and for 3 kinds of distributions. In particular, this result implies the equidistribution for preimages and the periodical points. And in the proof of previous results, we need to investigate thermodynamic formula for subsystems and use their equivalent state to obtain the suitable bound. Okay. Those are this is a reference here. This paper is the century of this talk, and those two study develop the thermodynamic formula for subsystems, and this one is for existence, and this one is for uniqueness. And in particular, this work partially extended this.
So the third one is for the existence, and the second one is for
right. Yeah, the second one is uniqueness, and the third one is for existence. Yeah, and we in particular we answer the 2 questions posted in the fourth paper by Professor Xianghui. Okay. So that's like the structure of the work. Okay, so thank you for your attention.
Yeah, thank you very much. Let's thank the speaker.
If any questions?
Yeah, let's start the discussion. Any comments or questions? Can you go back to these level 1 large deviation principles where you
okay,
where the rate function occurred? Yeah,
this one.
Yeah, I'm a little bit confused. I mean, if the set K contains the Birkhoff average, what is the rate function there infinite, or what is what happens with the rate function? Right?
Roughly, it's okay. Because the domain is R, right?
Yeah.
So roughly speaking, the graph of this rate function looks like this.
Oh, it's 0 at the.
Yeah, and this point is the correspond to the space average, and
I
at
see.
this point the rate function takes value 0, and in some parts it takes value infinity.
I see. So taking value infinity essentially means that the Birkhoff averages never visit this part of the space, right?
Yeah, because if you consider continuous function phi over a compact space, so this function phi is bounded, and if this interval is outside the target of this potential phi, then this is empty set, so
Yeah,
it's correspond to infinity.
Okay, makes sense. Okay. Yeah, I mean,
Yeah.
your picture already kind of answers my second question, right? I mean, what can you say about this rate function in general, right? I mean, I think we discussed this when I was visiting in Beijing. Are there some kind of general properties that you have? I mean, you drew it as some kind of a convex function. Is this a property that is true in general?
I guess you are asking about the continuity property of this rate function.
Yeah, continuity and convexity properties. So is there some kind of statement that you can make?
Yeah, what I can see is that in our setting for all expanding Thurston map, if we consider like a holder continuous function phi, and which is non-trivial, means it's not it cannot be written as a coboundary. I mean, roughly speaking, phi cannot be a constant. Okay, then we can see that this rate function I is real analytic and strictly convex on its domain.
Yeah, I see.
Sorry. For real analytics, you should stay in the middle, not stay away from its effective domain. Okay.